you are looking at a storm. Not a storm in the way you understand storms. Not the kind that knocks out your power for a few hours or floods a coastal city. This storm is so large that if you could somehow transport the entire Earth, all 7 continents, all the oceans, every mountain range and desert and forest and city where humans have ever lived, and drop it into this storm's center, it would disappear into the clouds like a marble tossed into a whirlpool. And the storm would not notice. For at least 190 years, and possibly much longer, this colossal vortex has been churning in Jupiter's atmosphere, feeding on itself, devouring smaller storms that wander too close, its crimson clouds swirling in an endless, counterclockwise dance, visible from 500 million miles away. We call it the Great Red Spot, and the more you learn about its true scale, the more you realize that the word great might be the understatement of the solar system. To understand the Great Red Spot, you first have to understand Jupiter. And to understand Jupiter, you have to forget almost everything your intuition tells you about planets. When we think of a planet, we imagine something like Earth, a solid ball of rock with mountains you can climb, oceans you can sail, a surface where you can plant your feet and look up at the sky. Jupiter has none of this. There is no surface. There are no mountains. There is nowhere to stand. Jupiter is a gas giant, the largest planet in our solar system, and it is composed almost entirely of hydrogen and helium, the same elements that make up the Sun. In fact, Jupiter is sometimes called a failed star. If it had accumulated about 75 times more mass during its formation 4.5 billion years ago, nuclear fusion would have ignited in its core, and we would have a binary star system instead of a solar system with 8 planets. But Jupiter did not become a star. Instead, it became something stranger, a world that is mostly atmosphere, where the air simply gets denser and denser the deeper you go, gradually transitioning into a bizarre form of liquid metallic hydrogen under crushing pressures, with perhaps a rocky core buried somewhere deep within, though even that core appears to be partially dissolved, diffuse, fuzzy, as NASA scientists have described it, based on data from the Juno spacecraft. Jupiter is massive beyond comprehension. Its diameter is 11 times that of Earth, about 142,984 kilometers at the equator compared to Earth's approximately 12,756 kilometers. You could line up 11 Earths side by side, and they would just barely stretch across Jupiter's face. But diameter only tells part of the story, because volume scales with the cube of the radius. Jupiter's volume is 1,321 times that of Earth. If Jupiter were a hollow shell, you could fit more than 1,000 Earths inside it. And mass. Jupiter contains 318 times the mass of Earth. It is 2.5 times more massive than all the other planets in our solar system combined. Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, all added together, still would not equal Jupiter's bulk. This is a world that dominates its cosmic neighborhood through sheer gravitational authority. Its pull is so strong that it has captured at least 95 known moons. Its gravitational influence shaped the architecture of the entire solar system during the primordial chaos of planetary formation. This is the world that hosts the Great Red Spot, and this context matters because on Jupiter, weather means something entirely different than it does on Earth. On Earth, storms are temporary visitors. They form, they rage, and then, inevitably, they die. Consider Hurricane Katrina, one of the most devastating storms in American history. At its peak in August 2005, Katrina achieved Category 5 status with maximum sustained winds of 175 miles per hour. It was a monster by Earth standards, sprawling across hundreds of miles of the Gulf of Mexico, its destructive power fueled by unusually warm ocean waters. The storm killed nearly 1,800 people and caused $125 billion in damage. And then, within days of making landfall, it was gone. This is because hurricanes on Earth are fundamentally constrained. They draw their energy from warm ocean water, but the moment they move over land, that energy source is cut off. The friction of mountains, forests, and buildings tears at their rotating winds. The storm's organization collapses. Within 24 to 48 hours of landfall, even the mightiest hurricane is reduced to a disorganized mass of rain and diminishing winds. The longest-lived tropical cyclone ever recorded on Earth was Hurricane John in 1994, which existed for 31 days as it wandered across the Pacific Ocean. 31 days seems remarkable until you learn that the Great Red Spot has been continuously observed since at least 1831, and it may have been spinning for centuries before that. Why the difference? Jupiter has no surface. There is no land for the Great Red Spot to encounter, no friction to dissipate its angular momentum, no interruption in its energy supply. The storm simply keeps spinning, decade after decade, century after century, confined between two powerful jet streams, one blowing eastward to the south, another blowing westward to the north. That act like invisible walls, trapping the vortex at approximately 22 degrees south latitude. Jupiter rotates so fast, completing one day in just 9.9 hours, the shortest day of any planet in the solar system, that the Coriolis effect driving the storm's rotation is amplified far beyond anything experienced on Earth. The Great Red Spot is not merely surviving, it is thriving in an environment perfectly designed to sustain it. Now let us talk about size, because until you truly grasp the scale of the Great Red Spot, you cannot understand what you are looking at when you see those images from NASA's telescopes and spacecraft. The Great Red Spot is shrinking. This fact appears frequently in news reports, and it is true. Observations since the late 1800s show that the storm has lost more than half its original extent. But even in its diminished state, the scale remains staggering. In 1879, the first reliable measurements of the Great Red Spot indicated that its longest axis stretched approximately 39,000 kilometers, about 24,200 miles. To put that in perspective, Earth's diameter is roughly 12,756 kilometers. This means that in the 19th century, you could have lined up 3 Earths side by side across the Great Red Spot's length and still had room to spare. When NASA's Voyager 1 and Voyager 2 spacecraft flew past Jupiter in 1979, taking the first close-up images of the storm, they measured it at 23,335 kilometers across, still nearly twice Earth's diameter. By 2017, when NASA's Juno spacecraft swooped to within 9,000 kilometers of Jupiter's cloud tops, the Great Red Spot had contracted to approximately 16,000 350 kilometers, about 1.3 times the diameter of Earth. As of the most recent measurements, it continues to shrink at a rate of roughly 930 kilometers per year, and its shape has changed from an elongated oval to something more circular. But let us be very clear about what shrinking means in this context. The Great Red Spot is still wider than our entire planet. Every city, every ocean, every mountain range on Earth could fit within this single storm. If you drove a car at highway speed along the storm's edge, the journey would take weeks. If you could somehow stand at the storm's center and look toward its boundary, you would not be able to see it. It would be far beyond the horizon, thousands of kilometers away, and that is just width. What about depth? For decades, scientists suspected that the Great Red Spot was a relatively shallow phenomenon, perhaps just a few tens of kilometers thick. A swirl of colored clouds on Jupiter's surface, impressive to look at, but not structurally profound. The Juno mission proved this assumption spectacularly wrong. Using a microwave radiometer that can peer beneath Jupiter's opaque cloud layers, scientists discovered that the Great Red Spot extends approximately 300 to 500 kilometers below the visible cloud tops. To put this in human terms, the average depth of Earth's oceans is about 3.7 kilometers. The Great Red Spot's roots go 50 to 100 times deeper than that. Juno found that the Great Red Spot's roots go 50 to 100 times deeper than Earth's oceans and are warmer at the base than they are at the top, explained Andy Ingersoll, a planetary scientist at Caltech and a Juno co-investigator. Winds are associated with differences in temperature, and the warmth of the spot's base explains the ferocious winds we see at the top of the atmosphere. This is not a storm floating on top of Jupiter's atmosphere. This is a storm that reaches deep into the planet, a three-dimensional structure of immense vertical extent, driven by temperature gradients and jet streams extending thousands of kilometers below. Speaking of wind, how fast is the Great Red Spot spinning? On Earth, a Category 5 hurricane, the strongest category on the Saffir-Simpson scale, has sustained winds of at least 157 miles per hour. Hurricane Katrina's peak winds reached 175 miles per hour. These are winds capable of stripping the bark from trees, turning cars into projectiles, and reducing houses to scattered debris. The winds at the edge of the Great Red Spot reach 432 kilometers per hour, approximately 268 miles per hour. This is nearly 50% faster than the most powerful hurricanes Earth has ever produced. And these winds have been blowing continuously for nearly 2 centuries at minimum. They scream around the storm's perimeter in a counter-clockwise rotation, completing one full circuit approximately every 6 days. Near the center of the vortex, the winds are calmer, strangely stagnant in fact, with relatively little inflow or outflow. It is as though the storm has achieved a kind of dynamic equilibrium, its outer winds racing in an eternal circle, while its core sits in eerie stillness. Recent observations from the Hubble Space Telescope have revealed that the winds at the Great Red Spot's edge are actually speeding up. Between 2009 and 2020, scientists measured an increase in the outer ring's wind velocity from approximately 328 kilometers per hour to 353 kilometers per hour. Nobody is entirely sure why. The storm is shrinking, its rotation period is slowing, and yet somehow the peripheral winds are intensifying. Jupiter continues to confound our models. Perhaps the most mysterious aspect of the Great Red Spot is the question that seems most obvious. Why is it red? The answer is humbling. After centuries of observation, decades of spacecraft flybys, and years of dedicated study by some of the most sophisticated instruments humanity has ever built, we still do not know for certain what gives the Great Red Spot its distinctive color. Scientists have strong hypotheses, however. The leading theory, supported by laboratory experiments conducted at NASA's Jet Propulsion Laboratory, suggests that the red coloring is a kind of cosmic sunburn. Here is how it works. The Great Red Spot is an anticyclone, a high-pressure system where material rises from below. This upwelling pushes clouds of ammonia ice and ammonia gas high into Jupiter's upper atmosphere, much higher than the clouds elsewhere on the planet. At these extreme altitudes, roughly 8 kilometers above the surrounding cloud tops, the ammonia is exposed to intense ultraviolet radiation from the sun. When UV light strikes ammonia in the presence of acetylene, a hydrocarbon that drifts down from even higher in Jupiter's atmosphere, a photochemical reaction occurs. The molecular bonds break and reform into new compounds, complex organic molecules that scientists call chromophores. These chromophores absorb blue light and reflect red and orange wavelengths, creating the spot's distinctive hue. The Great Red Spot is extremely tall, explained Kevin Baines, a Cassini team scientist at JPL, who conducted these laboratory experiments. It reaches much higher altitudes than clouds elsewhere on Jupiter. The great heights both enable and enhance the reddening. The storm's vortex nature also plays a role. The swirling rotation traps these reddish particles within the storm, preventing them from dissipating into the surrounding atmosphere. Over years and decades, the chromophores accumulate, intensifying the color. But this explanation, while compelling, remains unproven. Other scientists have proposed that sulfur compounds, phosphorus-based chemicals, or other exotic molecules could be responsible. The Great Red Spot's color varies over time, sometimes appearing deep brick red, other times fading to a pale salmon, or even washing out entirely, becoming visible only as a pale indent in Jupiter's cloud bands. The chemistry behind these fluctuations remains poorly understood. What we do know is that the color is literally only skin deep. According to Baines' models, the reddish material is confined to the uppermost layers of the storm's clouds, perhaps the top 100 millibars of pressure. Beneath that thin veneer, the clouds are probably whitish or grayish, the same colors as most other Jovian clouds. The Great Red Spot, for all its fame, may be essentially a white storm wearing a red mask. When was the Great Red Spot first seen? This question sounds simple, but opens into a labyrinth of historical uncertainty. The traditional answer cites Giovanni Cassini, the Italian astronomer, who would later become the director of the Paris Observatory. In 1665, Cassini observed a dark oval on Jupiter at the same latitude where the Great Red Spot swirls today. He called it the permanent spot and observed it repeatedly over the following years, tracking its motion across Jupiter's face and calculating the planet's rotation period with remarkable accuracy. 9 hours and 56 minutes, just a few minutes off from modern values. Cassini's spot was observed intermittently until 1713, when it vanished from the historical record. For 118 years, no reliable observations of a prominent spot at that latitude exist. Then, in 1831, a spot reappeared. Astronomers began making regular observations, and by 1879, when the modern Great Red Spot came into popular prominence, the scientific community had accumulated enough data to begin systematic study. The obvious question: is the spot observed today the same spot Cassini saw in the 17th century? For centuries, astronomers assumed the answer was yes. The Great Red Spot was imagined as an impossibly ancient phenomenon, a storm that had been raging since before Newton published his laws of motion, before the founding of the United States, before the Industrial Revolution, a meteorological feature older than most human institutions. But a 2024 study published in Geophysical Research Letters by Agustín Sánchez La Vega of the University of the Basque Country and his colleagues analyzed the historical observations in unprecedented detail and reached a surprising conclusion. The permanent spot and the Great Red Spot are probably not the same storm. The evidence is subtle but compelling. Cassini's permanent spot moved across Jupiter's face at a different rate than the modern Great Red Spot. Its dimensions, as reconstructed from historical drawings, were significantly smaller, 2 to 3 times smaller on its long axis. Its behavior differed from what we observe today. From the measurements of sizes and movements, we deduced that it is highly unlikely that the current Great Red Spot was the permanent spot observed by Cassini, Sánchez La Vega explained. The permanent spot probably disappeared sometime between the mid-18th and 19th centuries. If this is correct, then the Great Red Spot we observe today is not 360 years old, but approximately 190 years old, first forming around 1831, taking shape over the following decades and coming into clear visibility by the 1870s. This is still an almost inconceivable duration for a storm. The Great Red Spot has outlived every human who has ever studied it. It was spinning when Darwin published On the Origin of Species. It was there during World War I and World War II. It has survived the entire space age, being photographed by every spacecraft to visit the Jovian system. But it is perhaps not quite as ancient as legend once held. And here is the humbling corollary. If Cassini's permanent spot disappeared, so too could the Great Red Spot we know today. The storm is mortal. It simply operates on timescales that make human life seem like the flicker of a match. The shrinking of the Great Red Spot has accelerated in recent years, and some astronomers have speculated that the storm could disappear entirely within our lifetimes. Since systematic observations began, the storm has lost more than half its east-west extent. In 1879, it measured approximately 39,000 kilometers across. Today, it spans roughly 14,000 to 16,000 kilometers, still wider than Earth, but dramatically reduced. Beginning around 2012, amateur astronomers noticed that the rate of shrinkage had increased, with the storm losing about 930 kilometers of width per year. Perhaps more troubling, in 2019, observers witnessed the Great Red Spot flaking, fragments of red cloud spinning off from the storm's edge and dissipating into the surrounding atmosphere. These events looked, to some eyes, like the beginning of the end. News reports speculated that the Great Red Spot might dissolve within decades. But not all scientists share this alarm. Philip Marcus, a fluid dynamics expert at UC Berkeley, who has studied the Great Red Spot for decades, has argued that the apparent flaking may simply be a surface phenomenon, interactions with smaller storms or eddies that pass nearby, not evidence of fundamental instability. The visible red clouds, Marcus suggests, may not accurately represent the size of the underlying vortex. The storm's waistline could be shrinking without its fundamental structure being threatened. The most recent Hubble observations, spanning 90 days from December 2023 to March 2024, revealed another surprise. The Great Red Spot is not shrinking smoothly. It oscillates. Over the observation period, astronomers led by Amy Simon of NASA's Goddard Space Flight Center watched the storm expand and contract rhythmically, jiggling like a bowl of gelatin. The oscillation has a period of roughly 90 days, and nobody knows what causes it. While we knew its motion varies slightly in its longitude, we didn't expect to see the size oscillate, Simon said. As far as we know, it's not been identified before. That was very unexpected, and at present there are no hydrodynamic explanations. Simon's team predicts that the Great Red Spot will eventually stabilize in size, becoming more circular and more compact, confined within its latitude band by the jet streams that have held it in place for so long. Right now, it's overfilling its latitude band relative to the wind field, she explained. Once it shrinks inside that band, the winds will really be holding it in place. The Great Red Spot may not be dying. It may simply be evolving, adjusting to conditions we do not fully understand, transitioning to a new equilibrium state. Or it may indeed be approaching the end of its existence, preparing to follow Cassini's permanent spot into oblivion. We do not know. Jupiter keeps its secrets. What would it be like to witness the Great Red Spot in person? No human spacecraft has ever descended into Jupiter's atmosphere. The Galileo probe, released in 1995, plunged into Jupiter's clouds and transmitted data for 57 minutes before being crushed and vaporized by the increasing pressure and temperature. But that probe entered through a relatively clear hot spot, far from the Great Red Spot itself. We have never sent anything directly into the storm. Based on what we know, the experience would be overwhelming and brief. Imagine descending through Jupiter's upper atmosphere. The air is composed mostly of hydrogen and helium, with traces of ammonia that would be immediately lethal to breathe, even if the temperature and pressure were somehow comfortable. The clouds around you are not water vapor, but ammonia ice crystals, tinted with mysterious organic compounds that absorb blue light and reflect red. The pressure climbs. On Earth's surface, atmospheric pressure is approximately 1 bar. At Jupiter's cloud tops, it is already similar, but drop 100 kilometers and the pressure is 10 bars, 10 times what you experience at sea level. Drop another 200 kilometers and it is 100 bars. The gases are becoming thick, almost liquid in their density. The temperature is rising too, from a frigid minus 145 degrees Celsius in the upper atmosphere toward oven-hot conditions below. If you were somehow protected, descending toward the Great Red Spot itself, you would encounter the storm's churning cloud banks, towering walls of ammonia ice and ammonium hydrosulfide, painted in shades of white and orange and red. Lightning flashes illuminate the depths, 3 times brighter than lightning on Earth. The winds scream at nearly 300 miles per hour, racing around the vortex in an endless loop. Descend further, past 500 kilometers, and you would reach the storm's roots, the point where the great red spot circulation finally fades into the surrounding atmosphere. Here, temperatures approach 370 degrees Celsius. The air is so dense that it behaves more like a fluid than a gas. There is no surface below you, just more atmosphere, getting hotter and denser until thousands of kilometers down, hydrogen itself transforms into a metallic liquid. No human-built machine could survive this environment for long. Jupiter's radiation belts would fry unshielded electronics. The temperatures would melt conventional materials. The pressures would crush any vessel we could currently construct. The Great Red Spot exists in a realm fundamentally hostile to human presence, a permanent reminder that the universe contains wonders that we can observe but never truly touch. Why should any of this matter to someone standing on Earth 628 million kilometers away at closest approach? The Great Red Spot offers a window into atmospheric physics on a scale that simply does not exist on our world. By studying this storm, scientists can test theories about fluid dynamics, vortex behavior, and atmospheric circulation in an environment where the familiar constraints of our planet, solid ground, shallow atmospheres, seasonal interruptions, do not apply. But there is something more. The Great Red Spot confronts us with scale. It forces us to reckon with the fact that Earth, for all its significance to us, is a small world orbiting a medium-sized star in the outer arm of an ordinary galaxy. Jupiter alone could swallow more than 1,000 Earths, and Jupiter itself is modest compared to the stars. Our Sun contains 99.86% of all the mass in the solar system. When you look at the Great Red Spot, you are looking at a storm that is older than any nation, any institution, any living thing on Earth. You are looking at a phenomenon that has churned continuously, while empires rose and fell, while entire species emerged and went extinct, while all of recorded human history unfolded. The storm does not know we exist. It does not care. It simply is. And yet, we have sent spacecraft to study it. We have aimed the most powerful telescopes ever built at its swirling clouds. We have spent decades trying to understand its structure, its composition, its past, and its future. This storm, ancient and indifferent, has become a focus of human curiosity, a mystery we are slowly unraveling, a challenge we continue to accept. There is something profound in this. The universe is vast beyond comprehension, filled with phenomena that dwarf everything we have ever known. The Great Red Spot is just one such phenomenon, a single storm on a single planet, in a single solar system, among hundreds of billions of solar systems, in a single galaxy, among hundreds of billions of galaxies. We are impossibly small against this backdrop, but we are also the part of the universe that asks questions. We are the atoms that have arranged themselves into beings capable of wonder. And when we look at Jupiter's crimson tempest, spinning eternally 500 million miles away, we are the universe becoming aware of itself. There is a painting hanging in the Vatican, created in 1711 by the Italian artist Donato Creti. It depicts an evening landscape in Italy. Gentle hills, trees silhouetted against a darkening sky. Figures in period dress going about their lives, but looming in the heavens above this pastoral scene is Jupiter, rendered with scientific accuracy under the supervision of the astronomer Eustachio Manfredi. And there, on Jupiter's face, is a spot. It is red. This is the earliest known artistic depiction of a colored spot on Jupiter, created more than 3 centuries ago, before photography, before spaceflight, before we had any way to truly understand what we were looking at. Manfredi had likely corresponded with Cassini or studied his published observations. He knew there was something there, something permanent enough to warrant inclusion in what was meant to be an astronomically accurate painting. What did those 18th century astronomers think when they peered through their primitive telescopes at that distant world and saw a spot that returned again and again with each rotation? They had no framework for understanding atmospheric dynamics on such a scale. They did not know Jupiter was a gas giant. They did not understand the fluid dynamics of rotating vortices. They simply observed, recorded, and wondered. In a sense, we are still doing the same thing. Our instruments are vastly more powerful. The Hubble Space Telescope orbiting Earth, the Juno spacecraft circling Jupiter, ground-based observatories with adaptive optics that can compensate for atmospheric distortion. Our theoretical models are sophisticated enough to run supercomputer simulations of Jovian atmospheric dynamics, and yet the Great Red Spot still surprises us. It oscillates when we expected it to be stable. Its winds accelerate when we expected them to slow. Its color changes for reasons we do not fully grasp. The universe remains larger than our understanding of it. Let us return to Juno, the spacecraft that has given us our most intimate view of the Great Red Spot. Named after the goddess who could see through the clouds that Jupiter, the god, wrapped around himself to hide his misbehavior, NASA's Juno mission arrived at Jupiter on July 4, 2016, after a 5-year journey from Earth. The spacecraft entered into a highly elongated polar orbit, swooping close to Jupiter's cloud tops during each orbit before swinging back out into the relative safety of distant space. This orbital geometry was deliberate. Jupiter possesses one of the most intense radiation environments in the solar system, generated by charged particles trapped in its enormous magnetic field. This magnetosphere is 20,000 times stronger than Earth's and extends millions of kilometers into space. The radiation is so intense that it would destroy unshielded electronics within weeks. By approaching quickly, gathering data, and then retreating, Juno could survive long enough to accomplish its scientific goals. On July 11, 2017, Juno made its first close flyby of the Great Red Spot, passing approximately 9,000 kilometers above the storm's cloud tops, closer than any spacecraft had ever come. Its microwave radiometer instrument peered through the clouds, measuring thermal emissions at 6 different frequencies, each sensitive to different depths in Jupiter's atmosphere. What Juno saw transformed our understanding of the Great Red Spot. Before this flyby, the storm's vertical extent was largely unknown. Some models predicted it was shallow, perhaps 100 kilometers deep, a surface phenomenon sitting atop Jupiter's much deeper atmosphere. Other models suggested it might extend much further down. The microwave radiometer data revealed that the Great Red Spot's roots penetrate to at least 240 kilometers below the cloud tops, and possibly as deep as 500 kilometers based on gravity measurements taken during subsequent flybys. We're going to have to rethink the whole picture of what's going on inside this thing, said Scott Bolton, Juno's principal investigator from the Southwest Research Institute, after analyzing the initial data. The gravity measurements were particularly revealing. As Juno passed over the Great Red Spot, its velocity changed ever so slightly, by just 0.01 millimeters per second, due to the gravitational pull of the storm itself. By measuring these tiny velocity shifts with exquisite precision using NASA's Deep Space Network, scientists could calculate the mass distribution within the vortex. The results indicated that the Great Red Spot is relatively dense compared to the surrounding atmosphere, a coherent structure extending deep into Jupiter's interior. Juno also discovered that the storm is warmer at its base than at its top. This temperature gradient is crucial because it drives the powerful winds that define the Great Red Spot. Heat from below tries to rise, cooler air from above tries to sink. The rotation of Jupiter deflects these vertical motions into horizontal ones, generating the storm's characteristic spinning motion. The warmth at the base explains why the winds have persisted for so long. There is a continuous energy source feeding the vortex from below. Where does this heat come from? Jupiter radiates approximately 1.7 times more energy than it receives from the Sun. The planet is still slowly cooling from its formation 4.5 billion years ago, and this internal heat drives much of its atmospheric dynamics. The Great Red Spot, in some sense, is a heat engine, a machine for transporting thermal energy from Jupiter's depths towards space, powered by the slow contraction of a world larger than 1,000 Earths. The Juno mission also observed dozens of other storms on Jupiter, providing context for understanding what makes the Great Red Spot unique. Jupiter's atmosphere is filled with vortices. Some are cyclones, low-pressure systems that rotate clockwise in the southern hemisphere. Others are anticyclones, high-pressure systems that rotate counterclockwise, like the Great Red Spot. Both types form regularly, merging, splitting, and dissipating as they interact with Jupiter's jet streams and with each other. In March 2000, astronomers observed something remarkable. 3 white ovals in Jupiter's southern hemisphere, each a significant storm in its own right, merged into a single, larger vortex. This new storm was initially white, but over the following years, it began to develop a reddish tint. Scientists nicknamed it Red Junior or Oval BA. Today, it remains the second largest anticyclone in Jupiter's atmosphere, about half the size of the Great Red Spot. The fact that Oval BA turned red offers support for the sunburn hypothesis of chromophore formation. As the merged storm grew larger and its cloud tops reached higher altitudes, more ammonia was exposed to ultraviolet radiation, producing the same photochemical reactions believed to color the Great Red Spot. If you want to turn a Jovian storm red, apparently, you need to push it high enough into the atmosphere to get sunburned. But Oval BA also demonstrates the dynamic nature of Jupiter's storm systems. The 3 white ovals that merged to form it had themselves formed in 1939, when a previously stable atmospheric feature broke apart. Those ovals persisted for more than 60 years before combining. The new merged storm has now existed for more than 2 decades and shows no signs of dissipating. This suggests that the Great Red Spot, for all its uniqueness, may not be fundamentally different from other Jovian anticyclones, merely larger, older, and more favorably positioned between powerful jet streams. Perhaps it too formed from the merger of smaller storms, though so long ago that no observations of the process survive. Perhaps the permanent spot Cassini observed in the 1600s was a different merger event, a different generation of vortex that eventually dispersed, only to be succeeded by another. Jupiter's atmosphere, it seems, is always generating storms. The Great Red Spot may be exceptional in its longevity and size, but it exists within a broader ecosystem of vortices, a planetary scale pattern of formation and dissolution playing out across eons. One question that often arises when discussing the Great Red Spot is whether such a phenomenon could ever occur on Earth. The short answer is no, not anything close to this scale or duration. Earth's atmosphere is thin and shallow compared to Jupiter's, extending only about 480 kilometers above the surface before fading into the vacuum of space. Jupiter's atmosphere is tens of thousands of kilometers deep, with no clear boundary at all, just a gradual compression into exotic fluid states far below the clouds. Earth has a solid surface. When a hurricane makes landfall, it loses its energy source, warm ocean water, and encounters friction that rapidly depletes its angular momentum. The longest a tropical cyclone has survived on Earth is 31 days. The Great Red Spot has been spinning for at least 190 years. Earth's Coriolis effect, the deflection caused by planetary rotation, is modest compared to Jupiter's. Our planet rotates once every 24 hours. Jupiter completes a rotation in under 10 hours. This faster spin rate amplifies the Coriolis effect, helping to stabilize rotating vortices and confine them to specific latitude bands. And Earth simply does not have the thermal output to drive persistent storms. Jupiter radiates more energy than it receives from the Sun. Earth does not. Our weather is almost entirely solar-driven, and the Sun's energy input varies with day and night, with seasons, with latitude. Jupiter's internal heat provides a more constant, if mysterious, power source for its atmospheric engines. Perhaps the closest Earth analog to the Great Red Spot is not any individual storm, but rather certain persistent atmospheric features like the polar vortices or the persistent high-pressure systems that dominate subtropical ocean regions. These features can last for years or decades, though they are constantly evolving and do not possess the well-defined boundaries of a discrete vortex. They are patterns in the flow of air, not self-sustaining storms. The Great Red Spot exists because Jupiter is fundamentally a different kind of world, a world where the conditions for such a phenomenon are not just possible, but in some sense, inevitable. Given enough hydrogen, enough helium, enough mass, enough rotation, enough internal heat, and enough time, something like the Great Red Spot will form. It is an emergent property of gas giant planets, written into the physics that govern fluid dynamics on planetary scales. What will happen to the Great Red Spot in the coming decades and centuries? We do not know. The historical record shows a pattern of shrinkage. From 39,000 kilometers in 1879 to approximately 14,000 kilometers today. If this trend continues linearly, the storm would disappear entirely within a few decades. Some researchers have speculated that we might witness the storm's final dissolution within our lifetimes, an event that would be scientifically fascinating, but also, in some way, melancholy. But linear extrapolation of complex systems rarely works. The Great Red Spot has surprised scientists repeatedly over the years. Its color fluctuates, its shape changes, its winds accelerate, it jiggles and oscillates in unexpected ways. Predicting its future behavior based on past trends requires assuming that the underlying dynamics will remain constant, an assumption that Jupiter seems determined to violate. Amy Simon, who leads the Outer Planet Atmosphere's Legacy program that monitors Jupiter annually with the Hubble Space Telescope, has suggested that the Great Red Spot may eventually stabilize rather than disappear. As it shrinks, it is transitioning from an elongated oval to a more circular shape. Once it becomes small enough to fit entirely within the latitude band between its confining jet streams, the winds that have been squeezing it may instead act to preserve it. The storm could reach a new equilibrium, smaller, rounder, but still recognizable as the Great Red Spot. Computer simulations by Philip Marcus and his colleagues have explored possible future scenarios. In some models, the Great Red Spot shrinks and eventually dissipates. In others, it stabilizes. In still others, it persists for centuries more, slowly evolving, but never quite disappearing. The outcome depends sensitively on assumptions about Jupiter's internal structure, the behavior of its jet streams, and the properties of the small eddies that constantly interact with the storm's edges, factors that we cannot yet measure with sufficient precision to make confident predictions. One intriguing possibility: even if the current Great Red Spot disappears, another large anticyclone might form to take its place. The jet stream configuration that traps the Great Red Spot at 22 degrees south latitude existed before the current storm and will presumably continue to exist after it. If this region is inherently prone to generating anticyclones, and the formation of Cassini's permanent spot suggests that it might be, then the end of the Great Red Spot might simply be a transition to a new storm, a new generation of vortex spinning at the same latitude. We might be observing not a unique dying phenomenon, but a recurring feature, a location in Jupiter's atmosphere where great storms arise, persist for centuries, and then give way to successors. The Great Red Spot of the 20th and 21st centuries might be the third or fourth or 10th such storm to occupy this niche, each one rising and falling on timescales that dwarf human civilization. There is a final dimension to the Great Red Spot that rarely receives attention: what it tells us about storms on worlds beyond our solar system. We now know of more than 5,500 confirmed exoplanets, worlds orbiting stars other than our Sun. Many of these are gas giants comparable in size to Jupiter, and some orbit so close to their host stars that they are tidally locked, presenting one face perpetually to the stellar furnace. These hot Jupiters have atmospheres heated to thousands of degrees, with weather patterns unlike anything in our solar system. But others orbit at distances that would allow temperatures similar to our own Jupiter. And if the physics that generates the Great Red Spot is universal, if it follows from general principles of fluid dynamics rather than from some peculiarity specific to our Jupiter, then we might expect giant anticyclones to exist on gas giants throughout the galaxy. We cannot yet image these exoplanetary storms directly. Our telescopes are powerful, but resolving features on the face of a world orbiting another star remains beyond current capabilities. But we can infer atmospheric properties from the spectra of light that filters through these worlds' atmospheres during transits, and from the thermal emissions they radiate into space. Future missions and telescopes, the James Webb Space Telescope, already in operation, and larger instruments being designed for the coming decades, will expand our understanding of exoplanetary atmospheres enormously. We may eventually characterize the weather patterns on worlds hundreds of light years away, identifying the signatures of storms and vortices from the subtle variations in their light curves. When that day comes, the Great Red Spot will serve as our template, our Rosetta Stone for interpreting what we see. Every insight gained from studying Jupiter's giant storm, every model refined by Juno's measurements and Hubble's observations, will contribute to our ability to understand distant worlds we can never visit. The Great Red Spot, in this sense, is not just a local phenomenon. It is a case study in planetary science, a natural laboratory for atmospheric physics, a lesson that we will carry with us as we reach outward toward the stars. Whatever we learn here, we will apply there. 500 million miles away, the Great Red Spot continues to spin. It does not know that creatures on a small rocky world have named it, studied it, sent machines to photograph it. It does not care that it appears in astronomy textbooks, on NASA websites, in the dreams of children wondering what it would be like to fall into those endless clouds. It simply exists, as it has existed for centuries, as it may exist for centuries more. The winds rage at the storm's edge, the clouds churn in their eternal dance. Deep within the vortex, temperatures rise as you descend, driven by the slow cooling of a planet that was born when our sun was young. The chemistry happens, ammonia breaking apart, acetylene reacting, chromophores forming that thin red veneer over the whitish depths. The jet streams blow, confining the storm to its latitude band, squeezing it from north and south like hands pressing against a balloon. None of this happens for us. None of it has anything to do with humanity. The Great Red Spot would exist if no conscious being in the universe had ever looked up and noticed it. It is a feature of physics, a consequence of the laws that govern matter and energy, emerging inevitably from the conditions present on a massive gas giant planet in the outer reaches of a yellow dwarf star's gravitational domain. And yet, we have noticed, we have looked up, we have sent our instruments and our questions across the void. We have spent centuries puzzling over this distant storm, gradually assembling our understanding from observations made with equipment ranging from 17th century brass telescopes to 21st century interplanetary spacecraft. The Great Red Spot does not need us, but we seem to need it, or at least we need what it represents. We need mysteries large enough to humble us. We need phenomena that exceed our intuition and challenge our models. We need reminders that the universe contains wonders we have not yet understood, puzzles we have not yet solved, scales we can barely imagine. The Great Red Spot is one such reminder. It is far from the only one. The cosmos is full of objects and events that dwarf human experience. Black holes, neutron stars, galaxy clusters, the cosmic web itself. But the Great Red Spot occupies a special place in our awareness because it is visible, Accessible, a feature on a planet that anyone can see with the naked eye on a clear night. Look up, find Jupiter in the evening sky. Know that within that bright point of light, larger than 1,000 Earths, a storm has been raging since before your nation existed. And know that you, an impossibly small creature on an impossibly small world, are part of a species that reached out and tried to understand it. That is not nothing. That may be everything. Before we close, let us consider one more perspective on scale, a thought experiment that might help you truly internalize what the Great Red Spot represents. Imagine you are standing at the edge of the Great Red Spot's vortex, not on a spacecraft hovering above it, but somehow suspended within the clouds themselves, at the boundary where the storm's rotation meets the surrounding atmosphere. From where you stand, the wind is moving at approximately 432 kilometers per hour, roughly 268 miles per hour. This is faster than the fastest winds ever recorded in a tornado on Earth. The air around you is not air as you know it. It is mostly hydrogen and helium with traces of ammonia that would be immediately lethal to breathe, even if the temperature and pressure were somehow comfortable. The clouds around you are not water vapor, but ammonia ice crystals, tinted with mysterious organic compounds that absorb blue light and reflect red. Now begin walking. You are walking into the storm, toward its center. At your modest pace of perhaps 5 kilometers per hour, you cross the outer ring of the vortex, where the winds are fastest. The clouds swirl around you in an endless counterclockwise motion. Hours pass, then days. After 24 hours of continuous walking, 120 kilometers, you have barely made a dent in the distance to the storm's center. The edge of the Great Red Spot is still visible behind you, and the center is still thousands of kilometers ahead. You keep walking. A week passes. 2 weeks. You have now walked nearly 1,700 kilometers, roughly the distance from New York to Miami. The storm still stretches before you, vast and featureless. The same churning clouds, the same relentless wind. After a month of walking, covering approximately 3,600 kilometers, you might finally be approaching the storm's center, the relatively calm eye where winds drop and the atmosphere achieves a strange equilibrium. Behind you, the edge of the storm is now so distant that it would be invisible even on a clear day on Earth. You have traveled farther than the width of the continental United States, and you have not left the storm. Now consider this. While you were walking, the Great Red Spot itself was moving. Jupiter rotates in under 10 hours, and the storm drifts slowly relative to the planet's bulk. The landscape you are traversing is not stationary. It is being carried along by planetary forces, rotating around Jupiter's axis, subject to jet streams and pressure gradients and thermal convection. You are walking across a moving platform larger than your homeworld. This thought experiment, absurd as it is, since no human could survive even a fraction of a second in Jupiter's atmosphere, begins to convey what we mean when we say the Great Red Spot is large. It is not merely larger than Earth in some abstract statistical sense. It is a territory. It is a region. It is a place where, if you could somehow walk through it, you would spend a month traversing its extent. There is another way to think about the Great Red Spot's significance. In terms of time rather than space, the storm has existed for at least 190 years, and possibly much longer. Let us be conservative and use that 190-year figure. What has happened during the lifetime of this storm? When the Great Red Spot first became clearly observable in the 1830s, Charles Darwin had not yet published On the Origin of Species. The American Civil War had not been fought. The telephone had not been invented. Electricity was a scientific curiosity, not a utility. Antibiotics did not exist. Human life expectancy in most countries was around 40 years. The storm has been spinning while the Industrial Revolution transformed human civilization. 2 world wars devastated continents. Empires rose and fell. The British Empire, the Soviet Union, the Third Reich. Humans learned to fly, then to fly faster than sound, then to leave the atmosphere entirely. We split the atom. We developed computers, then the internet, then artificial intelligence. We cured diseases that once killed millions. We doubled our global population, then doubled it again. Every human being who was alive when the Great Red Spot first became prominent has died. Every human being who saw it through a telescope in the 19th century has died. Most of the humans who studied it in the 20th century have died or are elderly now. Generations have been born, lived their entire lives, and passed away, while this storm has continued spinning. The Great Red Spot has no awareness of any of this. It does not mark anniversaries. It does not remember the past or anticipate the future. It is a physical phenomenon, obeying the laws of fluid dynamics, sustained by temperature gradients and jet streams, and the angular momentum imparted by Jupiter's rotation. But we can mark these things. We can remember, we can recognize that the storm we observe today is the same storm that Giovanni Schiaparelli studied in the 1870s, the same storm that astronomers photographed through the earliest astronomical cameras, the same storm that the Voyager spacecraft imaged in 1979. There is a continuity here that transcends individual human lives. In a sense, the Great Red Spot is a monument, not built by anyone, not commemorating anything, but enduring nonetheless. It is one of the few natural phenomena in our solar system that has persisted recognizably across multiple human generations. A landmark in the sky that our great-great-grandparents could see, and that our great-great-grandchildren may still be able to see. Not many things last that long. Mountains erode, rivers change course, even the continents drift. But this storm has been faithful to its location, its nature, its slow and steady rotation for longer than most human institutions. The study of the Great Red Spot is ultimately the study of atmospheric dynamics under extreme conditions, conditions that cannot be reproduced in any laboratory on Earth. Scientists who model the storm use equations that describe the conservation of mass, momentum, and energy in a rotating fluid. These are the same equations that govern hurricanes on Earth, jet streams, ocean currents, and the circulation of our atmosphere. But on Jupiter, the parameters are different. The Coriolis effect is stronger. The vertical extent is far greater. The energy source is not solar heating, but internal planetary heat. By applying our models to the Great Red Spot and comparing their predictions to observations, we test whether our understanding of fluid dynamics is truly universal. Every successful prediction builds confidence that the physics works everywhere, on Earth, on Jupiter, on exoplanets we may never visit. Every failed prediction reveals gaps in our knowledge, pointing toward new research directions. This is how science works. We observe, we model, we test, we revise. The Great Red Spot is one of the most valuable test cases we have, precisely because it is so extreme. If our models can explain a storm 300 kilometers deep, with 400 km/h winds persisting for centuries on a planet with no surface, then perhaps we truly do understand something fundamental about how fluids behave in rotating systems. And there are practical applications too. Understanding atmospheric vortices helps us predict hurricanes on Earth. The same numerical methods used to simulate the Great Red Spot are used to simulate terrestrial weather systems. The insights flow both ways. Techniques developed for Earth weather forecasting informed Jovian research, and discoveries made at Jupiter illuminate phenomena here at home. The Great Red Spot is not just a curiosity. It is a research tool, a natural experiment conducted on a planetary scale over centuries, generating data that no human-designed experiment could ever replicate. We return, finally, to that first image. You are looking at a storm that could swallow the world you call home, a storm older than your nation, your culture, your language, a storm driven by forces you can describe with equations but may never fully comprehend, a storm that has been observed by humans for centuries and will likely be observed for centuries more, assuming we remain a curious species capable of building telescopes and pointing them at the sky. The Great Red Spot asks nothing of you. It makes no demands. It offers no warnings or promises. It is simply there, rotating at 22 degrees south latitude on a planet named after the king of the Roman gods, indifferent to all the small dramas playing out on the small worlds scattered throughout the cosmos. But if you are the kind of person who looks up at the night sky and wonders, if you are the kind of person who wants to understand not just your immediate surroundings, but the vast context in which you exist, then the Great Red Spot has something to teach you. It teaches humility. Your entire world is smaller than this storm. It teaches persistence. This storm has outlasted every empire, every institution, every individual who has ever observed it. It teaches mystery. Despite centuries of observation and decades of spacecraft exploration, we still do not fully understand why the storm exists, why it persists, why it is red, or what will happen to it. And it teaches wonder, because when you truly grasp what you are looking at, when you internalize the scale, the duration, the complexity, the sheer improbability of such a phenomenon arising and persisting in the universe, you cannot help but feel something. Call it awe, call it perspective, call it the overview effect without ever leaving the ground. The Great Red Spot does not care whether you feel these things, but you are human, and humans are the part of the universe that feels. We are the atoms arranged in such a way that we can contemplate other atoms arranged in storms the size of worlds, spinning in atmospheres thousands of kilometers deep, on planets we will never touch. That capacity for contemplation, for reaching across 500 million miles with our minds, even when our bodies remain rooted to this small rock, may be the most remarkable thing about our species. The storm will keep spinning whether we watch or not, but we watch anyway. And in that watching, in that wondering, we become part of something larger than ourselves, connected across space and time to everyone who has ever looked up at Jupiter and asked the same questions we are asking now. What is it? Why is it there? How How long will it last? And what does it mean that we, of all the arrangements of matter in the universe, are the ones asking? The next time you see Jupiter in the night sky, that brilliant point of light, brighter than any star, wandering slowly among the constellations, remember what you now know. Remember that inside that point of light, a storm larger than Earth has been raging for nearly 2 centuries. Remember that winds faster than any hurricane blow around its edges. Remember that its crimson clouds tower 8 kilometers above its surroundings, baked by ultraviolet light into complex organic compounds whose exact chemistry we still do not understand. Remember that we are small and the universe is large, and there are wonders beyond counting waiting to be understood. The Great Red Spot does not care if you remember, but you might find that you cannot forget.